Okay, great. So I think this will be probably the last presentation for today. Um, so basically, I'm going to show you some like tech demo, like the open source Grandmaster timing card, and then I'll take the opportunity also to show you a little bit more like about the we call it time machine. It's right behind me, and like a bunch of other things that basically we had to build on our way as we were like basically exploring these things with my colleagues. And so without further ado, we'll just jump into it. So basically on the right, you see here, this is the time machine. And like this was like actually the time card, like the first prototype we had. And then we basically went ahead and did like a lot of iterations. But on this time machine, basically you have all these like servers. We have like a range of different hardware. We have basically Broadcom's P2100G, we have Mellanox CX6, we have the Intel E810, we have even like some FPGA like Corundum things. We have like we're practicing like cold storage. We're testing like our Wedge 100, the existing thing, and then the upcoming one, Wedge 400, and like different concepts for Grandmaster. Like one of them is basically based on a rubidium miniature rubidium clock, and the other one is actually a CSAC. So it's like a cesium clock actually. And all these machines are, I mean, thanks to all this extra pressure that we got from working from home and like being pushed basically like to do everything remotely. You never know when you're gonna use your privileges to come back to lab. So we try to automate as much as possible the system. For example, here on the right side, you see this matrix. This matrix has basically all the PPS inputs and outputs coming in, and you have like 128 by 128 like inputs and outputs, and you can choose like any output to be like any input. Like one input can go to all 128 output or anything else. Like it's basically, if I want to show you here, let's see, if I show you my entire screen, desktop share, like basically I have this matrix and I can choose any output to any inputs. Very exciting. Like this is repurposing an old device that was basically used for video stuff. It's funny, I bought this thing like $100 off eBay. There are a bunch of other ones. So hurry up, go snag your own before they realize what kind of gem this thing is and will increase the price. So basically, you have like different inputs and outputs. Like for example, I can connect the PPS input for, let's say, this card C1R5 to, let's say, to my Grandmaster or like to this Calnix Neo or any other thing. I can do any combination I want here. It's very interesting. Like I have even my measurement tools here, like make it to prove this thing is working. I probably will show you, I will mess up with my system here. I think the oscilloscope should be pin 30. I have them all named, labeled like properly. First time I do something properly, I guess, in naming. Like usually I'm not a big fan of that. So let's say here, channel 2, like let's say channel 3 or channel 4. Channel 4 is a green. Channel 4 is right now connected to the OGM PPS output. I will basically plug it to the, you see the green should like right now fade off. Let's see, green disappeared with something else. I can connect basically this thing to, let's say the GPS PPS input. Like this is before, so this is from the GPS. And you can like make all these changes and so on. And I have also my like Paragon device here. So the Paragon, same thing here. Paragon is connected here. I can connect Paragon to any input, to any output, do all this measurements. So without being in the lab, I can have all these connections basically. So the Paragon right now is actually testing our timing card versus a Cesium clock. So there's a Cesium clock coming also in to have, and this is like this glitches from remote. Like you're right now watching remote on screen share. So like basically here, like you see, like it's within, I'll say less than 50 nanoseconds, basically things are going in nanoseconds here. So Paragon T is also doing here. We have Paragon like Neo. We have all kinds of things like basically on this device. It's really, I consider myself blessed to have like all this hardware that I can play with. So going back to our presentation, we came up also with another interesting tool. We're calling it Ptp Box. So Ptp Box basically has 7 CX6 cards. You can put any other card. And what is happening is because we figured out how to do the boundary clock, transparent clock, ordinary clock, all of this basically PTP4L, we have all these NICs isolated with namespaces. So it's very interesting. You can just run the servo inside and then communicating with another NIC. Like you have these devices virtualized, but they're not virtual, they're real. So like the servos can run independently on each one of them. You can basically try a clock tree. You can try different methods for servo, PI, I don't know, linreg, all kinds of things. And then at the same time, you can pull, let's say if you're using a Mellanox CX6 special card that has the PPS input and output, you can pull that all on an oscilloscope and see exactly what's going on. Very scalable. You can have any number of machines. I have basically a diagram of 5. So we made also another version. It was here. I probably lost it at home, I think. So which like basically we jammed everything in a tinier box. We call it actually Ptp Box Mini. So that one is based on a device called Protectly, which we repurposed it. That thing is designed for being a firewall, but then we basically just wiped off all the software that it was coming up with, and we added just CentOS, and then we ran this whole concept again. That one has E210 Intel cards, and you can basically, again, go between them. But again, I don't have access to the PPS output to do like these fancy oscilloscope stuff. So this one, serves whatever purpose it had. Like it helped us a lot actually learning about how PTP4L can perform in boundary clock. And this is where we also tested like designated master clock, all kinds of things. So again, back to the like timing card in action. So we have timing card basically sitting here. This was, I would say, the first prototype. This is the second one. And I have here 2 copies, and there's more. Like again, I had to basically hand solder these. It was a combination of, we needed the time, like we couldn't afford like waiting for a PCBA to put it together. And then I had to basically go part by part. Again, this is a tradition I have with my friends always. Like usually I start system by system to see what's going on. To my surprise, there were very little bugs. Like, I mean, like I think all these years of playing with hardware, all the way from low level to like, I don't know, to high level stuff, like it paid off. Like we learned a lot of things on our way. But still, there were like some, like, I don't know, mistakes that I can't believe I made. Like, for example, connecting the FTDI directly to the 5-volt instead of using the VUSB. So if you unplug it in between, put it back, the chip will hang. So also, because we had this whole thing, like basically starting from scratch, we had to build our own custom like PCIe panel. Here I have my talented friend, Spencer. He basically put these things together in, I'll say 2-3 days. Like it was really impressive, like how he basically put together all the designs, everything, like PCB, BOM, schematic, FPGA code, where you should get it, all the DigiKey shopping cart, everything is available for free. And you just write timingcard.com. How convenient is that? Timingcard.com. You wait for it, you get the GitHub, everything in your disposal. Like you have basically here the entire BOM, all the parts on DigiKey. You don't want to like go around it. Just press this button, and your cart will get ready. I can make another one for Mauser if we see like any other. If you guys want to do it, please do it, and then just like add it to this GitHub. It's open to everyone. We have the driver part. This driver is right now for CentOS. We're planning also to make a driver for Windows, so you will solve once forever the timing, hardware time stamping for Windows. We have a lot of teams like are interested. Again, for scientific application. We have the design, schematic, PCB, everything based on Altium. You don't have Altium, no problem. We have the PDF file. You can look at basically all like the CAD stuff. Fabrication, we have like all the Gerbers here available. We have the settings you need for the GNSS. Right now we're using this F9T from UBX. And here is again my famous napkin sketch style. Just
Ahmad,
like
Ahmad, quick note, you're showing still the presentation on the screen. If you think you're showing browser, this is
oh my goodness. Okay, thank you for telling. Okay, right. So I go here and share. And yeah, I should have. Thank you, Oleg. So desktop should. Yeah, probably missed a lot here. Okay, so again, going back to, as I said, you write here, timing card. You get basically to the GitHub, and you have again. Don't need to mention again. So you have the BOM, you have the driver, the ECAD fabrication, GNSS. You have the in the CAD, you have basically the brackets, and you have here about the FPGA. You have like the bit stream for the FPGA. You have the configurator, everything. Like this is where we work with our partners, NetTime Logic, and this is open for you to add as much as you like and change things. And then we are right now talking to different vendors to basically have this out of the box ready. If you cannot wait, great. You can get all these parts and then you go ahead. I'll probably set something on Tindi so you can order the PCB directly there. And Oleg already mentioned to you, like we have Aurelia, their own interpretation basically of this card available soon, if not already. Jumping back into the presentation, let's see, go back here and make it the presentation again. Presentation. So we have here, like, for example, I'm showing you like how you can put it together in a Tioga Pass Type 6 machine, which you have like basically a time card. Again, this one didn't have the bracket yet. I need to update for a new video. So click in. Simple as that. And the NIC of your choice. And voila, you have like an open source Grandmaster ready for operation. And just to make things a little bit funny, like basically here was a time lapse of me putting together one of the cards 500x. So we're basically joking about this. This is like our pick and place machine. 30 seconds you can have the time card. So yeah, there was a lot of like tiny 04, 02 and like 06 04, 0402s and then 0603s in terms of components. So coming next, like basically we put together basically the new SA45S CSAC. This is a Cesium Clock in a Pelican case with a battery. So this is more like of an experiment, but we're thinking like it's not bad to just have like a solid proof that, remember, like in my presentation, I mentioned that everything we're looking for is based on the PPS pulse you get from the GPS in a geographically distributed fashion. Like you're basing the hypothesis is the PPS signals are accurate enough so you can do all these things. This will be a proof. So basically, I will tune it, let's say in my location, and wait for it for a long enough time to have like everything synchronized properly. I can like test like the holdover where I have everything's working. Then I can ship it, let's say, to Oleg, and then Oleg receives it. He just connects PPS output, checks how it is with respect to, let's say, with respect to his machine that is synchronized with the PPS from his GPS. And then once he gets enough data, packs it without touching anything else, sends it back to me. I check again. Anything in between here, like we can assume like the drift was within that sandwich. And again, we can repeat it several times with 2 different machines or so on, with 2 different suitcases setups. So then we can have at least like a measurement of like, okay, this is how PPS looks like across the chart. So of course, because you're dealing with nanoseconds and you're traveling like with the airplane, everything, you have time dilation, you have all like other factors, which we will not go crazy right away, but slowly, once we see we have like some solid data we're getting just from the normal operation, we will like do all like fancy experiments, sending one this way, the other way, like up, down, like, I don't know, measuring, like keeping a log of the speed of the airplane as we go through and so on. So I will hand it to Oleg. He will show you some more demos or like in action, basically, a timing card.
Nice. Thank you, Ahmad. Just a second. Can you stop sharing the screen? Okay, so yeah, you can see, and yeah, my dog and my setup well, and some stuff here around. Anyway, so yeah, hi everyone, hi again. It's Oleg, just from the Grandmaster presentation. So thank you, Ahmad, for hanging it to me. It's basically, I wanted to show you that our time card in action, because it's one thing to show it in the slides, which may be somehow prepared in ideal conditions, and another thing is what exactly you can get if you build it yourself or if you basically buy it from vendor. But you can still get such amazing things in your home environment, basically. So let me quickly guide you through the environment I actually have here. So this is a normal PC, nothing fancy. It's one, yeah, actually from the office. I managed to recover it. So yeah, nothing special. If we open it, we will see the magic sauce, basically. So let me remove this. Okay, so what do we have here? We have basically our time card, right? So this is the thing which does all the magic. And as you can see, there are some diodes on the bottom. So this is the GPS receiver, which has a blue PPS, and the time card itself has a red PPS and some other status diodes, which I described in the spec. But basically, this is how we know that everything is functioning right now, and I can see it because 2 diodes are in sync. Okay, it has something is not okay with the stream, or can
I'm able to see that.
Okay,
looks
yeah.
great. Looks great.
Yeah, video looks great. Go ahead.
Rajiv, any comments? Do you see the video?
Video looks great, but I'm just looking at the live streaming session, and we don't see that.
Okay, sorry about this. Hold on a second, and then let's do another thing. Okay, guys, can you see and hear me now?
Yes.
I don't know.
Yes,
okay.
And this should work. Yeah.
Okay, so sorry about this. Some technical details. I will quickly go over again. There is nothing. I didn't show anything special yet. So again, this is my PC from the office. Nothing fancy. I already opened it. It was closed, but that's the only thing you basically missed. So we have a time card which is installed here. You can see it. And it has some diodes there, which are in sync, as I said already. And those diodes basically show PPS. The blue one shows PPS from the GPS receiver or GNSS receiver U-block we use. And there is also red diode, as well as some status diodes, which are defined in the spec on the GitHub. Please go and contribute there. So you see they're in sync right now, which means the PPS on the GPS receiver is in sync with the PPS on the time card. Okay, then we have a time card. There is atomic clock as well. There is JTAG to reprogram FPGA, which is also on board. And there is USB UART to basically have some interactions, get some status info and more. There are also extra sockets, the power ones. For example, you can see there is even no power socket connected right now because it's just, yeah, it's not consuming too much power. But we have this option if you use, for example, more expensive or heavily loaded atomic clock. Then we also have Mellanox network card. So this is CX6 100G interfaces. I would say this is not a typical for a home usage, but it doesn't really matter actually in this case which network card you use. It just gives you higher precision or lower precision, and yeah, makes you look fancy. And there is also a Wi-Fi plug, so I can do the demo anywhere I want. Then other than that, it's just a normal PC. There is a CPU, the RAM and whatnot, nothing special. So if we go on the back of this PC, what we see is basically, this is an antenna, the one which basically provides the PPS, as the GPS signal and other GNSS constellations. And there are also two outputs, which are actually the PPS. So we can compare the PPS coming out of the card and PPS coming out of the GPS receiver. So this is just purely for the debug and demonstration purpose. Normally those two would be disconnected, and antenna is connected, obviously. Then there is the Mellanox network card. You see there are two interfaces connected to it at the moment. For sake of demonstration, I will show you later on. And antenna for Wi-Fi to connect to this box. Then we also have the USB converter. So for GTAC, so we can actually basically flash the firmware with just USB. And the UART. So nothing fancy. Okay, all of this goes, why all of this is connected? Because it goes to a very precise device, which is called Calnix Sentinel. And with this device, we actually were able to demonstrate the impact in a real lifetime without any fancy editing. So if I click on the screen, I activate it. So the measurement is happening right now. And actually you can see it happening already for almost 6,000 seconds, right? So it's for a long time I have this measurement running. So what you can see is the first thing you see, it's in nanoseconds. If you can see it on the screen, I mean, I know it's like showing the screen from the mobile phone, but you kind of can imagine, trust me, this is nanoseconds. And then if you go back, if you zoom out again, those two lines are basically those two PPS outputs from the time card. So the purple one is a GNSS receiver PPS. So how off this pulse per second compared to true time, which is at this moment on the Calnix device. So at this moment, the GPS PPS compared to the true time is between 60 and 40 nanoseconds away from absolute zero. This is basically within error rate of the GNSS receiver itself. And then we have a time card, which is a blue one, which is after all of the processing is actually better for some reason compared to true time than the GPS receiver itself. That's an amazing job that NetTime Logic did for us. So we have this, and this is output of PPS. What we can do, you can see there are 4 channels. So this is the time card, this is the GPS receiver, and there are 2 channels as well. Those channels are actually the NTP and Ptp channel. So we measure both of them at the same time. On the server, which is on your left, as you remember, we run Crony as an NTP server and Ptp4l as Ptp server. So going back to our measurements, we can actually switch to another mode, which is showing the protocol, basically difference. As you can see, this now is in microseconds. So you can see here. And it shows that the offset for NTP, which is blue, is around 10-ish, between 5 and 15, so around 10-ish microseconds from true time. And this is NTP. This is insanely good for NTP, to be honest. I mean, we work with NTP for a while. But what is also outstanding is the purple line, which is Ptp. First thing you notice, and this is actually very important, look how stable it is. Even without going how precise it is, we know how stable it is, because it's always staying at the same level, which can give you some guarantees, some SLAs, anything you can promise, compared to NTP, which is spread all over the place, even with such awesome precision. What we can do now is basically click here and switch to a bit more detailed node. You can see what exactly the last value is. So for Ptp, in this case, it's 1 microsecond, and for NTP, it's about 9 microseconds. So this is the current state. What is also interesting in this, we can actually observe more or less the same thing on the server itself without super fancy hardware. So if we switch a bit to my laptop screen, I will not start sharing it, but I will just show it again. So this is the server I connected to this PC box next to me. So on top, you see the PHT2Cs. That's exactly what's copying data from the time card to the network card. So as you can see, the offset is in single numbers of nanoseconds. So while we are copying data from time card to the network card, we are losing maybe single numbers of nanoseconds. You can see it's moving. It keeps moving. So it synchronizes all the time. And on the bottom, you can actually see the NTP. So NTP, this is the PHT clock. Compared to, and you see how precise it is. Chrony estimates that the error rate is just 17 nanoseconds, so it's plus minus 17 nanoseconds. And then we also compare it to public NTP, which we run. Remember, the server is connected via Wi-Fi, so wireless network. So we have around, around 10 milliseconds, maybe 15 milliseconds. But this is because of the Wi-Fi, obviously. But it still shows you how shitty, sorry for the slang, NTP is and how good PTP is.
This is impressive, Oleg.
Basically it, what I wanted to demonstrate at this moment. So,
one thing I like to add here is the way that the time card advertises itself is very nice, like, because it doesn't need any extra hardware. So it basically advertises itself like a PTP enabled NIC, with the exception that it has 0 ports and it only has a POSIX clock, basically the PTP clock. So you don't need any extra like, let's say, software or something. You simply use the PHT2Sys. You just treat it as just like basically copying one NIC to the other, and like and you can take advantage of like the fact that this is running on an FPGA. Right now, you saw like Oleg had basically these two cables, the red cable and that colorful cable for the JTAG. Coming soon, we have a quasi flash basically sitting on the FPGA, so you can program the FPGA directly from the PCI bus, like firmware updates. You still need the cable if you put, like, let's say, a faulty image and quote unquote brick your card. And that red also, we are basically swapping that red USB cable to go again via the PCIe bus, using like the AXI drivers to directly like have COM ports in the system and working further. Again, work in progress, and we are really calling for action. We want to have you guys basically be part of this whole journey as we're going through. We don't want to go alone through this. We want to have like the community backed by this. That's the whole purpose. We want to have all fun together. And this basically brings me to this slide for call for action. Again, Oleg, do you want to add anything to this before we wrap it up?
So yeah, it just goes to show that there is not much actually. Basically, anyone can, using open source components which are already on GitHub, anyone can basically implement this. Anyone can get the timing card. It's my favorite example is a researcher in Siberia, right? You can still be there far, far away. You have no access to very expensive hardware. Then you build it yourself. It's not that difficult. And remember, from Napkin Sketch, which was there 3 months ago. From 3 months ago, we ran live demo, which we're sure about, that we know that actually Calnex super precise certified device will show how awesome this is. And we are so sure about this. So anyone can do it. Please join us. Let's make it together.
Wonderful. Yeah, so again, I have it here, timingcard.com. Like, I don't think it's gonna get more convenient than this. Simply timingcard.com. Okay, I think that's about it. Rajiv.
All right. So it's 11:30. So all right.
Any questions? Maybe we can go to like if there's any question or comments, or I appreciate it, whoever stayed with us. It's almost like 3 hours and a half, right?
Yeah.
Yeah, pretty much.
I think I already showed you guys, or not, like it's an example of one of these timing cards, and you have it, you have all the pictures there, but these things are real. So, and these PPS input, output, you can configure them to whatever you want. Like you can basically have 4 timestamps, basically 4 events, external events that they can occur. You can accurately timestamp them. You can imagine what things you can do. You have like an extra GPS, GNSS receiver you can put there for increasing reliability. We have here basically 2 footprints for SI time oscillators you can add here. We have TDCs in hardware. We have PLL you can add in hardware. We have an RTC that you can add for, again, if you want to have like just like one other layer of like accuracy. These 2 connectors, Oleg mentioned to you, were one that designed, so like the card Oleg was showing you, it was using the 12 volts straight from the PCI bus. But if you want to just do on like without plug in the card there, still will use a GPS, and it will like basically tune to nanosecond accuracy with FPGA and everything. You can power basically the card via these connectors. And also what else you can do is like you can keep like a UPS system for this in case that the server goes down, the clock stays up, so it will not require additional time basically to do the locking and like the synchronization and everything. So that's why we are calling this a time card. In terms of the driver, we have a DID 0x400, and it can be any vendor on the other side. With the help of our kernel team, we have the driver basically coming up in the mainstream kernel, upcoming kernel. So you don't need any additional driver for it if you're a Linux user. So basically just the latest kernel, you plug this card, you have everything. You can use the design, everything that we have here, and then basically take your own interpretation or derivation of like this design and have your own thing. That's why we're calling it a generic time card.
Thank you, Ahmed. Thank you, Oleg. This was a great live demo. And the first contribution coming out of TAP is workstream number 1, the Open Grandmaster. What a great teamwork. And
Thank you.
for everyone involved. I think that brings us to the end of the day, end of the TAP track, and we will see you all on Wednesday, 11 a.m.